for organizing this contest and challenging us and trying to push us harder and challenge our limits. Then we like to thank everybody else for their support throughout the whole project. And lastly, the sponsors who helped us to get here actually, the government of Romania, Vanessa Shopping City, and Ropeco. Thank you for your attention. We can go. Okay. Shall we take this one? Okay. Okay, thank you.
Okay, I think we're a little ahead on the schedule, which is always nice. So, but let me go ahead and get started, and let me pull that up. Yo, what would just happen? Okay. So our next presenter, as we're systematically going through, there is an order to what we're doing here. So the point where we're looking at now is actually the chemistry. And Jeff Greenblatt he comes to us from Berkeley, where he lives, and actually went to UC Berkeley there, got a PhD in chemistry. He has worked at NASA Ames Research Center, Princeton University, the Environmental Defense Fund, as well as Google. So when I have problems, can I talk to you about my Gmail? No. Oh, okay. You can refer me. He is known for energy analysis, climate policy, and sustainable transportation. And since 2014, he started a company, Emerging Futures, that focuses on these emerging technologies. And until recently, he's worked at Lawrence Berkeley National Laboratory for 8 years. He was focused on multi-decadal economy-wide modeling of greenhouse gas reduction strategies and other emerging technologies, including artificial photosynthesis and autonomous vehicles. He's widely published in these fields. And his current focus with Emerging Futures is building simulation models of large-scale interconnected space ecosystems, including human habitation, mining operations, and material production on the Moon and Mars. So his presentation right now is producing chemicals as needed and other useful chemicals, including organic polymers on the Moon. So welcome, Jeff.
Thank you, Doug.
Yeah.
Great. You can kind of see the evolution of my interests a little bit. So kind of a segue from the Earth-focused work I've been doing the last 15 years or so to apply it to space. So this was an opportunity for me actually to learn a bit about how plastics are made and the many other useful organic chemicals that you sort of have to make on the way to plastics, which winds up being an incredible diversity of chemicals that we're really quite dependent upon for our modern civilization. So what I'm going to talk about is what you get when you set making some polymers as your end goal from the resources that we find in situ on the Moon. So why do we need plastics at all? Well, it has a wide range of functions. I won't read through all of these here, but it is another machinable material like the metals that we're talking about, but they obviously are a little bit softer. But they can be extruded, machined, molded, etc. They have some really nice properties. Some of them are really great at providing air or watertight seals. They can be food compatible. They can have strong chemical resistance for acids or bases or other kinds of things like that. They come in flexible shapes, and they can have some nice things like these repeatable deformations, like a hinge for a pop-top bottle. That's actually quite a bit of technology there. And what else did I want to say here? And they can be used to make clothing and textiles, since we're not going to have a whole lot of agricultural activity, presumably at first, mostly focused on growing food. Where are you going to get your clothing, coverings, and other materials like that are soft? And so plastics, as we know, are increasingly a part of our life there already. How much plastic do people use and need? So this is a hard question to answer. It varies tremendously across the world. I mostly dealt with data that I could find in the US as a starting point. But of course, this includes a lot of plastics that are really not used very mindfully, because you buy a bottle of something in the store and you throw it away. There's some plastic recycling, but not nearly as much as there could be. And so the question of how much we would actually need on a self-contained base, we probably won't be buying and throwing away plastic water bottles, for instance. But there is a lot of stuff that we might need to make from polymers that are made from things like cotton and other organic materials on Earth. There would be a substitute. So I'm sort of on the order of 100 kilograms, which is actually how much plastic the average US consumer consumes right now. It's broken out by sort of the top 10 or so plastics shown in this pie chart here. And sort of the top 4 things that we're all very familiar with are peat, polyethylene terephthalate, regular polyethylene, which is what fleece jackets are made of, polypropylene, and polyvinyl chloride, PVC, for pipes and things that have replaced a lot of the plumbing. And then a whole bunch of others that are sort of roughly 20% or so. So even if we have reduced need for packaging and higher recycling, we might need these plastics for other things that aren't really used on Earth today, but it's possible that this could be reduced significantly. So maybe on the order of 10 kilograms per person per year, but we just don't really know. So we'll kind of keep it at 100. Now, what are the elements that are in most polymers? So clearly we have carbon and hydrogen, as you would probably guess, since they're mostly made from petroleum as a starting material on Earth. We also have important amounts of nitrogen and oxygen in the array of polymers, and a not insignificant amount of chlorine. Now, all of these can be derived from different resources on the moon. I'm showing you that you can get obviously hydrogen and oxygen from water. You can also get oxygen from the regolith oxides that are being reduced, producing a lot of free oxygen. And there are important amounts of chlorine in the regolith, although there's a lot more on Mars apparently. But there is enough that we could extract, although that may wind up being a limiting reagent in some cases. Nitrogen we don't need a lot of, but they are really key. And nitrogen is actually a very important chemical for a lot of intermediate chemicals, solvents, and things like that. And so you'll see its role there, sort of starting with ammonia. But carbon is the most important element of all of these for making polymers. And so what we found from the L-Cross and LAMP experiments that were done in circa 2009, 2010, is a kinetic impact at the lunar South Pole to verify the presence of water ice, which we found in about 5.5% concentration mixed in with the regolith there. But we also found a lot of other volatiles in addition. And I have a breakdown by element shown on the left, and I'm sorry it's a little too small to read, but I can just tell you basically half of it is water, and the other half is things like hydrogen sulfide. I'm just kind of going around here. Hydrogen sulfide, ammonia, SO2, different hydrocarbons like methane and ethylene, carbon monoxide, and even some free hydrogen gas there. And by element, you're looking at on the order of about 0.7% carbon by mass and more than 2% hydrogen, and these other things are significant amounts. So contrary to what I thought originally, there is actually quite a lot of hydrocarbons embedded if we can get these from the regolith. And presumably when you're extracting the water, basically by heating it up to turn it into a vapor, these gases will come along as well, and then they can be effectively separated and used. So as I said, all of these are already in the polar regolith, in the polar regions. In addition, the regolith that's mixed with it is going to contain chloride salts, and the rest would be shipped off to the metal refinery that would extract aluminum, iron, titanium, and other things like that. And then the question is, how do we go from here to the polymers? Well, with some simple chemical conversions, we can get there. And I'm going to show you the eye chart that shows the work that I've been doing over the last couple of months to try to map out the simplest pathways to get from starting materials to final product without having to make sort of crude oil, which is how we start on Earth to make these things. So it's basically looks like the design of a complex chip, I guess. What I'm showing here is on the left are the raw materials. Most of this is coming from the lunar volatiles that I talked about, but also there is some regolith salts shown sort of down near the bottom. I have NaCl. It's not really in that form, but it's basically ionized, so it's positive and negative ions that are mixed in with other minerals that can be extracted fairly easily, I think. And then at the bottom, I just kind of throw in, for fun to think about, there are also some polymers that are starting to be made from biological products. And so I have lactic acid as an example that can come from certain plants that can be turned into polylactic acid, which is actually a biodegradable plastic. We don't use a lot of this today, and its applications are a little limited, although it is used for 3D printing in some cases. On the right are a bunch of common polymers of varying complexity, but you can see some of the names. They're almost all familiar to you, some more than others. We've also got things like epoxy, two-part epoxy, which is obviously a very useful polymer for all kinds of applications, gluing and so on. And even things that are more sophisticated like Kevlar at the bottom, which is a little harder to make. But in the middle, what you see is sort of the process pathways, and in among these are a whole bunch, well, there's water and oxygen, which sort of you do first. And there's going to be plenty of oxygen produced as a byproduct. But then you have all of these useful inorganic materials, things like concentrated sulfuric acid, hydrochloric acid, sodium hydroxide, chlorine gas, and of course all the things on the left that are useful in their own, ammonia and so on. And then along with this, we're also making a whole bunch of useful organic chemicals. These are used as solvents, or used as intermediates for making lots of other kinds of things. So if you can make, essentially, if you can make a few sort of C1, 2, and 3 carbons, things like ethylene and propylene, and then you can get to benzene, which is a fairly straightforward process once you've made straight-chain hydrocarbons that are similar to crude oil, kind of here. You can essentially then, with a few extra organic synthesis steps, make most of the other components you need. So the idea is that in making these, you wind up also with these reservoirs of other chemicals that are used for cleaning, for dissolving things, and even for synthesizing like needed medicines that might be required. So I focused on the polymers, but there's a lot of other things that you could kind of go down that road and say, well, how much acetone would you need? How much methanol? How much other sort of organic solvents for different kinds of processes? But that's a much, much larger endeavor. So then the question is, how much can we actually make? What is the limiting factor if we're also doing other things with this reservoir of lunar ices? And the answer very clearly is water. It's all going to be limited by, or it's actually being governed by the amount of water that the colony needs. And so in conversation with Doug about the things that the colony needs, so obviously drinking water and sanitation, hydration for crops that you're going to be growing, but really the big thing is the propellant that you're occasionally going to need to get people and materials off the surface. And so with some pretty conservative estimates of how often people would leave, and I forget what it was, Doug, was it like 1 trip every year per person, something like that? It turns out that the vast majority of the water you need is going to be for that sort of very occasional trip. Everything else is shown in there. Most of the rest is actually for agriculture. Of course, you're recapturing and reusing this water, but with that less than 100% efficiency. And that very thin sliver at the top is the intrinsic human needs. So it's really dominated by propellant and how much you have to move things around. The picture would change, of course, if you decide never to leave the moon. But we kind of assume, at least at the beginning, that you're going to be moving around a bit. And so the price tag is really quite high. It's about 30,000 kilograms per person per year to provide the water that you need. So that's the amount, and most of that is lost in space because, of course, you're using it as propellant. So that is the amount that you have to mine and purify every year in order to provide for a person's needs. Now, it turns out that there's quite a lot of hydrogen trapped in that regolith mixture as well. And so that actually reduces your requirements by quite a bit because you can use the hydrogen that's free plus the hydrogen that you get for electrolysis. And then you need a little bit less water mining, but you still have extra oxygen that you have to get. So maybe you get some of that as a byproduct from the metal refining. In any case, maybe I can reduce this total amount to roughly 12,000 kilograms. I'm sorry, I didn't put the number on. But that maps out to quite a bit of additional water that has these volatiles trapped in it. And in total, because water is only about 5 or 6% of the total mass of the regolith that you're mining, we're still looking at mining about 170,000 kilograms of sort of mass in total. So what you have is this superabundance of metal oxides that you can use for other things along with the water mining and everything else. And in terms of what that then means for the plastic reagents, you have a huge surplus. So with the roughly 10,000, sorry, so it was actually closer to 10,000. I did some refined calculations. With the roughly 10,000 kilograms of water also comes about 7,000 kilograms of other stuff. 440 kilograms of ammonia, 1,200 kilograms of carbon in various carbon-containing molecules, and then about half a ton of other materials, hydrogen, oxygen, and sulfur, that are actually really not needed for very much. Plus, along with that, you get almost 10 kilograms of chlorine in the regolith that's mixed up with that. So the question is, how much can you make with that? And the answer is a lot. The limiting reagent seems to be the amount of carbon. This is a chart showing the ratio of how much you have to how much you need to make the 100 kilograms per person per year of plastic that I had showed a couple of slides ago. And you have the least amount of carbon of all the elements. And with that, you can make 15 times the plastic that you need. Now, I will say as a caveat, we do seem to be somewhat limited by chlorine. If we use as much chlorine in PVC plastic as well as intermediates as we do on Earth, we might have to look for additional sources of chlorine. But I think we could also sort of switch the relative amounts of different plastics and get around that problem. We may also find that there's more chlorine than we had estimated. But with that, essentially the picture is the following. Assuming that we have 8 permanent inhabitants in a sort of an initial base, we would be mining nearly 1.4 million kilograms of icy regolith per year. And in that is now going to be 75,000 kilograms of water, a like amount of other volatiles, and that amount of chlorine. It produces this much hydrogen for the propellant mostly, and this much oxygen, which is gotten from this variety of means, what's in the water and then what's mined as a regolith byproduct. And then nitrogen and carbon are on the order of 3,500 and nearly 10,000 kilograms per year. And so kind of the big picture is that we can make more than 10 times the plastic that we actually need, based on my sort of rough estimate based on how much a US citizen consumes. But of course, I was also assuming that there wouldn't be any waste along the different synthesis steps. So let's be more conservative and say that we lose, I don't know, we lose 20%, for every step, because you're not going to capture it all. 5 minutes left? Okay, great. Plenty of time, so I can kind of riff on this in the last bit here. But I think even if you assume that you're going to be losing a lot in each of those steps, really the most complicated synthesis that I showed was maybe 10 synthetic steps, and so maybe you would have on the order of 5 or 10% of what you started with. That's still more than enough in order to provide for all the plastic needs. And we probably will have a fair amount of recycling and sort of rejiggering of what people actually need. And so I think the bottom line is that there is more than enough raw materials just mixed in with the regolith to provide all the plastics that the colony could provide, to provide air and water sealing, to provide containers for toxic chemicals, food packaging and preservation, seals, clothing, etc., and still have lots of other materials around to make those solvents, acids, bases, and other industrial chemicals that you need to do the other parts of living and working in space. And so it actually paints a rosy picture of what might be possible, and this is without having to import anything from Earth or from other resources in space. So in conclusion, and I've kind of already said that, I guess, there is much more than we need, and careful recycling and reuse can make this resource go even further. And maybe we would get to the point where we can create stockpiles of materials, or maybe export some hard-to-make materials into space that are a lot cheaper to provide from the moon than, say, from the Earth with its much deeper gravity well. And so finally, I am happy to take any questions you have. I don't know how many people remember this scene, but the future is in plastics.
Any questions for Jeff? Just raise your hand.
Yeah.
If you consider what kind of plastics are more appropriate for the colonies, the ones that don't end up in the air scrubbers, which ones would be appropriate for background?
So, sorry, so you're asking specifically appropriate for,
For being on a moon colony, being in a vacuum situation, being in an enclosed environment where the air has to scrub out some of the volatile.
yeah, good point. I have not thought very much about the outgassing that happens from some of these plastics as they're, once they're produced. I assume, or I am aware that there are these additives that are made, that are placed in a lot of plastics as, to sort of subtly change their chemical properties, and these are volatile, and so they come out, and in a closed environment they can definitely build up. Yes, there would need to be a lot of scrubbing of the air of those materials. However, I will say that the human body also exhales a lot of organics that we don't really want to build up either. I mean, I'm talking about things besides CO2. And so there's going to need to be a lot of air processing and separation as well. What I can say, though, sort of putting an optimistic spin on it, is if we already have the infrastructure set up to separate these materials from the lunar ice, and then when you're doing the various chemical transformations, you're capturing the various streams of products, major products and side products that a lot of these chemical reactions produce, you're going to be well equipped to be able to recapture and reuse other volatiles that are in the air supply and condense them for reuse. So maybe I can put it that way. But I'll just say one other thing, which is in terms of what kinds of plastics are more appropriate, many of these plastics, they have multiple applications, and it's really just about economics as well as maybe what people prefer, cost-wise, or if it's something that you're wearing against your skin, it's what has a better texture. Many of them do have sort of interchangeable properties. There are very few plastics where you can only use that one material and nothing else. Even something like Kevlar, there's a lot of chemical analogs that are similar. But let's see. All right, I'll call on you first.
So, noting that you did the analysis for 8 persons,
Yes.
you looked at what the maximum population you think could be supported.
Well, that's maximum population. So again, this is assuming continual extraction of that lunar ice and essentially assuming that you're kind of losing all of it. Now, again, if you have very good organic recovery, then the supply that you have could go a long way. But you're still digging up the water anyway, provided, assuming that you still are launching things into space. I know that the estimates of how much water is on the moon varies depending on who you ask, and I think the more optimistic estimates are on the order of 2 or 3 billion tons. That's a lot of people years, even if I'm taking 30 tons per person per year. So I would say you could support a colony of millions of people with this.
Actually, if I can speak to that.
Sure.
The estimate is that if you do the ISS level of recycling of water, I'm not dealing with the organics, but just the water, the rough estimate is about a city of 1 million people for about 1,600 years. And in those 1,600 years, you could develop a means to be able to bring asteroids in. So basically, there's no limits.
And that includes the propellant applications as well?
No, it's just for local consumption. So you'd reduce that significantly.
I will say, and I know there's some people at the conference who will be presenting on this, a lunar space elevator would get around that problem, and that can be built with materials we already know how to produce as opposed to exotic carbon nanotubes. So was there a question over there? Yeah.
Yeah, it was a quick one. So, how long would it take you to start producing plastic pipes or sleeves?
Yeah, so I didn't have the time to really get into the, what I haven't talked about is how much equipment do you need in order to be able to produce all of this stuff, at sort of modest, sort of small industrial scale. And I don't have an answer to that. I do know from other ISRU work I've done that it's almost always the case that you can provide many times the mass of the equipment in a year's time in terms of material. And so I don't think that's really going to be a showstopper unless you have a very exotic process. So maybe back there. Yeah, in the gray. Mm-hmm. No, you, sir.
What's your next step in your research in terms of what are you doing next?
Thank you for asking. Yeah, I've actually this research endeavor has kind of opened me to thinking more seriously about the different things that you can make from lunar or Martian materials. And so I'm looking into understanding some of these pathways that are the most promising in more depth, because what I'd really like to do is identify one or two kind of polymers that can sort of give you as much additional stuff along the way as possible, and maybe be an opportunity to look into building some sort of a pilot demonstration. And yeah, on the end.
Arthur C. Clarke once wrote that our posterity would never forgive us for burning fossil fuels instead of saving them as base stock for plastics. It seems to me that our posterity may not forgive us for burning water off the moon as propellant instead of saving it as a base stock. Do you have any comments?
I think I would just repeat the earlier one, that this is chemical propulsion is what we have now, and it's a great way to get started. And we're not so much talking about a lunar economy here, but I think that it would really help growing a lunar economy. But long term, we're going to have to get away from that, because they are once use it once and it's gone. It's in interplanetary space. So yeah, and on the end here, yes. Was that okay?
I'm going to ask you to rethink what your requirements are, because you're focusing on what per person uses on Earth. And I'm thinking about the whole infrastructure to build the habitat in addition. And the way we're going to get around on the moon is probably with hoppers. And as soon as you have all those suborbital hops burning into your fuel supply, you're in a whole different place. And since carbon is the limiting factor, we're not going to be able to get it all out of the regular. But if we think ahead, all the containers coming up could be carbon, all the ones going back are platinum.
Yeah.
It's not have to get it
Platinum
all.
box. Yeah, I appreciate your comment on that. And yes, there's so many other things that we need to consider as well. And this is really just a first snapshot. As I said, I just had to kind of start with a number that gave us the right order of magnitude. And maybe it's not even the right order, but it's an order off to one degree or the other. But good point about other kinds of transportation on the surface. If we are using hoppers, that will consume a lot of water. Probably not the carbon, but hydrogen, oxygen. Yeah. Yes, Doug.
So actually, one quick reply, and then you'll have
As far as
stuff.
plastics outgassing, you might be able to put plastics outdoors in a vacuum and it might outgas faster. You should
True.
be sure. That's all.
True.
So you can hang around a little bit.
I will.
To answer more questions.
Sure.
Okay.
Okay, thanks, everyone.
Let me. Yes. Thank you, Jeff. So this track is Achieving Earth Independence, and we're going systematically. We haven't gotten to the food, for example. We've got two presentations on the food. So when is the second half of this track going to be? It's going to be Sunday afternoon. I don't know how many of you are going to be here, but I just wanted to sort of give you a heads up on what we're going to go through. We're going to go through artificial gravity and producing habitats. Obviously, you can't survive long term unless that artificial gravity is dealt with, and you need to produce habitats. How will food be grown? Bryce is going to present on that. And then Chris Wolf in the back, he's going to be talking about meat, nutrition, dietetic sorts of things. And then especially excited about Dr. Alex Ignatiev. He's going to be describing his research in the laboratory. He's gone all the way from regular simulant all the way to solar cells. So power production is something that's quite advanced. Dr. Alex Leyendecker, he's going to be speaking about the populations, children, family, those sorts of things, okay? And then Chris Meza from Tucson, he's going to be, this is something I want you guys to understand. This is a series of presentations. What we're wanting to do is during this next year, go ahead and take it to the next level, and that is actually do some of these projects. In the next year, can we develop a little hydroponic thing that takes the waste and be able to close the loop, at least on a small scale? Can we think about what equipment is needed, and can we demonstrate actual production